For lesson 10.3, we're going to take a look at hypothesis testing when sigma is unknown. Now, as we talked before, generally we are not going to know the population standard deviation, sigma. So instead of using z values, we're going to have to use t values. So which means we'll be running a t-test. In order to use a t-test, we still need a simple random sample. But in this case, sigma is unknown. And we still need a sample size of at least 30 or a population distribution that's approximately normal. Now, our adjusted formula for using a t-test statistic is x bar minus mu, and this time it's s divided by root n. So that should look really familiar from your z statistic. Then we're also going to need to use critical values of t. Remember, our critical values of z came from the small table in your yellow packet. We're going to need the t table, which is the bigger one. And in order to use that, we need to know the degrees of freedom. Remember, degrees of freedom is n minus 1. So you just have that here. Then we are going to use rejection regions today, and then tomorrow we'll talk about using p-values. But we are going to reject the null hypothesis if the t-value that we calculate is less than our critical value of t. That's for a left-tailed test. If our test statistic t is greater than our critical value of t on a right-tailed test, we reject. Or on a two-tailed test if it's on either end, basically more extreme than our t-value, our critical t-value. So we'll get an example here in a minute. So we want to find the critical t-score that corresponds with 14 degrees of freedom at the 0.025 level of significance for a right-tailed hypothesis test. So you need to look this up in your table. So go to your yellow paper to find these t-values. I don't have one, but I have something similar here. So we are going to go to 14 degrees of freedom. And then in one tail, we want 0.025. So that's like the 7th column over here. So down here, 2.145 is what I want. So our critical value of t is going to be 2.145. The next problem, we're going to do an entire test. That was just to show you, to remind you how to find your t-values. All right, nurses in a large teaching hospital have complained for many years that they are overworked and understaffed. The consensus among the nursing staff is that the mean number of patients per nurse each shift is at least 8. The administrators complain that the mean is lower than that. And the administrators are trying to prove their point, so they gather information from a simple random sample of 19 nurses' shifts. And the sample mean is 7.5 patients per nurse with a standard deviation of 1.1. So we want to test the administrator's claim at alpha is 0.025. So let's start writing our steps. Step 1, we need the null and alternative hypothesis. Now remember, it is the administrators, the hospital administrators, who are running this test. They are trying to show that the average number of patients is less than 8. The nurses are convinced it's greater than or equal to 8. Step 2, we have a simple random sample. We do not know sigma, which is going to suggest that we need a t-test. We don't have 30. N is not 30. It's only 19. But the number of patients per nurse is a normal distribution, so we're still okay. And our level of significance, we've already decided, is 0.025. All right, in step 3, we're going to calculate our t statistic, which from that formula is x bar minus mu over s over root n. So we have 7.5 minus 8 over 1.1 divided by the square root of 19. It's negative 1.98 when you calculate that. All right, step 4 is we need to make some decisions. So we have our normal distribution. That was terrible, sorry. And our alternative hypothesis is less than, so this is a left-tailed test. So we want to know, does our t statistic, this negative 1.98, does it fall in the rejection region? So we need to look up our critical value of t. With 19 shifts, that means our degrees of freedom is 18, and our alpha is 0.025. So I'm going to go back over to my table, 18 degrees of freedom, 0.025, it looks like 2.101. And since we're left, that's going to be negative 2.101. That's our critical value. So now we're going to take our test statistic, this guy, and see where that falls. So it actually falls here. That is not in our rejection region. So we are going to fail to reject the null hypothesis. Okay, so we have to accept the null hypothesis. So what this means is that the average number of patients, the data doesn't support that we can say that the average number of patients per shift is less than 8. So I'm not going to write all that down because my handwriting is terrible on this thing. But you're going to say something like at alpha equals 0.025, the data does not support that the average number of patients per nurse per shift is less than 8. So it appears that the nurses are right in this case. At least the administration hasn't shown anything. They haven't provided any data that supports that it's actually less. Okay, so the nurses appear to be right in this case. So that's how we do rejection regions. Very similar to what we did in 10.2, just you've got a slightly different process using the T's.